So gamma, right? So we know that this thing is ABC, right? And this thing is, well, it's complicated. All right? But we already figured out the gamma coordinate map with the previous problem. Oh. Bummer.
This is going to be wrong.
Yeah, it's going to be wrong because we had an error. But you can fix it if you want. So obviously, well, I mean, the error, basically these formulas have to be adjusted for the correct that I just erased, right? Okay, let me not belabor that point. I put bars here so that I can make the substitution without going nuts because I'm using A, B, and C in a different way. So basically I went back to the previous problem and replaced A, B, C with A bar, B bar, C bar so that I could look at like whatever's there as being A bar. So C is equal to A bar, B bar is equal to A plus 3B plus C and so forth, right? And that way I can make the substitution into these formulas, again corrected for the algebra mistake. And when I do that, I get a mess. But eventually, you get this, which again is going to be slightly off because the coordinate map was wrong. And then you can tilt your head and squint, right? Because you're taking some matrix, this, right? And out pops that stuff, right? So like minus 3 halves A, minus 5 halves B, you stick with the wrong thing, okay. Plus C, right? And then other stuff. So to get that first thing, what do I have to put? I have to put exactly minus 3 halves, minus 5 halves, and 1. Right? So that's why I do this down here. So I'm just reading, I'm thinking about this in my mind's eye. I usually write it down, but I didn't have space in the paper to write it down. You know, I would encourage you to write this down. It's helpful, you know. And so you have, and then the second one gives you 3 halves and 5 halves. There's no C, so there's a 0 here. And then it's 1 half and minus 1 half. There's no C, so there's a 0 there. Again, these will be wrong, I mean, because of the mistake in the problem. What was it, 8?
Yes.
Of course, I made a significant mistake as soon as I stopped grading. So if I had graded those 3 instead of the last 3, I would have noticed. Oh well. Now, alternatively, and I won't pick up on the mistake because my checking the answer is also based on the incorrect coordinate. But one of the other ways you could calculate the matrix would be, like, for example, the first column should be the coordinate vector of the first basis element. First basis element beta was x squared plus x. You calculate p of that thing, you get 0, 1, 2, 0. It's easy to go back to the definition and figure that out. And what's the coordinate of this? Well, you go back to the gamma coordinate mapping, and it pops out this thing, which of course is the first column, which is a good check. I mean, you could use, of course, this as a method to calculate the matrix, right? That's the other way you can do this, is calculate each column separately and just string them together. Just like we did before with the standard matrix, right? You can either calculate the whole thing at once from looking at the formula, or you could calculate T of E1, T of E2, T of E3, and just put them together. Then there's still those 2 methods here. Oh, there's more to this question. What's that?
Where did you put the 0, 1, the matrix 0, 1, 2, 0 to get the 3 halves?
Oh, I fed this to the coordinate mapping, the wrong gamma coordinate mapping from the previous problem, which told me to do complicated things to these 3 numbers to get those. I mean, I have to add them and divide by 2 or multiply by 3 or something. I don't have memorized. I look back at the previous page, plugged in A equals to 0, B equals to 1, and C equals to 2, and that's what popped out. Now, how do you figure out the rank of a linear transformation? Remember we talked about? The rank is the what? It's the dimension of the column space, or the dimension, or the nullity is the dimension of the null space of the matrix, as it turns out. Those are reasonable because it doesn't matter what coordinate system you choose, it's always, the dimensions preserved. here it's 3 and 0. And you can prove that lots of different ways. One way you can do is you can calculate the reduced echelon form of the matrix, and you get the identity, which would show you that it's full rank, rank 3. Or you could show that the kernel is 0 directly, if you wanted. That would also suffice to show that it has nullity 0 and rank 3. Because you know the total dimension is 3, so you can use rank nullity to only calculate half of that, right? Problem 10, I did not grade, but I wonder what you guys did there. I think the best way to do this is to kind of attack it directly. First of all, to prove it's a linear transformation, that is something you should all be able to do without like too much consternation on the test, all right? That part of this question is totally fair. The question of finding the inverse is a little nasty, okay? A little bit. So there it is, so I just feed it a linear combination, A1 plus A2, you transpose, property transpose, matrix algebra, bam, TA1 plus TA2. It's additive. And this similar argument shows it's homogeneous. Any questions about that? Yeah. Okay.
Could we just do that in one step, or would you prefer it done in two
Just
steps?
one step with you can
So
put
we
the
could say CA1 plus...
CA1 plus CA2. In fact, I prefer that. That's fine.
Okay.
Yeah.
Would we have to do CA1 plus CA2, or could we just do CA1 plus B2?
CA1 plus A2 is fine. Yeah.
If you do that, do you have to state the thing where it's like closed or like under addition and like if it's like one's equal to
I'm
0?
okay with you saying it follows that it's linear, since
Okay.
C and A1 and A2 are arbitrary. That would be fine with me. Yeah, okay. I hope we understand that means, we understand the sub-story there. That's you take C equals to 1, get additive, and take A2 equal to 0 to get homogeneous. I think I can let that go. All right, so to find the inverse, I go back to base principles. Like the way to find an inverse for a formula is to solve for the range variable. It's solve for the domain variable, taking the image as a variable, right? So like basically I set T of A equal to Y and I solve for A. And that gives me the formula for the inverse. T inverse of Y is B inverse Y, B inverse transpose, all of that. And then I prove that it's the inverse, right? How do you prove something's inverse? You just compose it both ways and show that it works. And it does, because transpose of transpose is what you get back to, and inverse times matrix is the identity. So, one way to prove something has an inverse is to give a formula and then to show that it satisfies the definition of inverse. We do a lot of indirect reasoning in here, but you should remember you can sometimes find a formula. This is such a problem. Where the indirect reasoning would be much harder, I think. The alternative way I would think about doing this would be to choose a basis for our 2x2, and then you could calculate the matrix, right? It would be a 4x4 matrix. You could show it's invertible. Showing that matrix is invertible would then allow you to argue that the transformation is invertible. Anybody use this argument?
You said not to.
I said not to.
Yeah, okay.
Oh, that's right. I don't advise that. If you can avoid that argument, do so. Problem 11. So the diagonal 4x4 matrices are like ABCD on the diagonal, 0 is elsewhere, right? The basis for the whole set of symmetric matrices looks like this. So you have the diagonals and then the off diagonals, sums of things above and below the diagonal, right? There's 10 possible things. In mission 6, we had a problem about the quotients dimension, where we learned that if you take the basis and you just select everything that's not in the quotient subspace, that those representatives form a basis for the quotient. So that's what I do. I take x plus w, where x is in the basis for the whole space with the quotienting space. In this case, b is s and w is d, right? And so that leaves me with something like this. And this is a typical thing in the quotient: AB 0 ABC, A 0 DE, B 0 F. So basically, the typical representative of this quotient has the diagonals set to 0 and the off diagonals are arbitrary. So if you look and you start counting, there's 6 things there, right? A, B, C, D, E, F. And so once you know that, you can write down the isomorphism, right? Not too hard. It's just, you just kind of, I mean, there's other isomorphisms to write down, but this is basically corresponding to, say, for example, taking this coset, right? E1, 2 plus E2, 1 plus D, and mapping it to x to the 5th. And then this coset maps to x to the 4th, this coset maps to x to, and so forth. But, I mean, for me, once I've written down an arbitrary point in the subspace in terms of independent parameters, then I usually can just kind of see how to write the isomorphism down just from just looking at it, you know? If I use the language find an isomorphism, you do not have to justify that it's an isomorphism. I really do just mean find on the test, all right? If I want you to find and justify it, I will say so. Okay?
So it'll say find and justify.
Yeah.
We found a lot of isomorphisms for like polynomials. Can you give an example where it wouldn't be like a P5 or whatever, it'd be like something different?
Yeah, sure. I could find an isomorphism to say R2 by 3. Blah. Same blah.
Okay.
And then I would just do A, B, C, D, E, F, like so. Isomorphism, for example. I mean,
Wait. Same blocks, but it's a 2 by 3. Is the block a 2 by 3?
no, the blah is the,
All of that?
and okay, oh, and you guys were like, this, oh, you know what, this is wrong. What am I missing? Oh, man, I should have, I did that.
The kernel is the
No. It's worse than that. Yeah.
Could you also do an isomorphism to,
It's okay, Chris. I mean, hold that question for a second. I need to address something. What I should have had is psi of 0, A, B, C, D, E, F. Okay, 0, 0, 0, B, yes. Thank you. A, B, C, D, F. Oh, that's an E. Oh well, go back to my Sesame Street again. Yes, I'm missing a big honking D right here. A D there. Because psi was supposed to be an isomorphism from the quotient space. This is not the quotient space. This is the original space. This is, I'm gonna go tear up this solution. Anyway,
So you should have put a plus D after?
plus D. No, there should be a plus D inside right here.
that's my.
Yeah.
Yeah. Should be like this,
Okay.
except to
Oh, okay, so you mapped that because you mapped that 4 by 4 to a 2 by 3.
well, there's really only
There's
1,
only
2,
six.
3, 4, 5, 6 free
So you
parameters
kind
here.
of only have to like account for those.
Right. I mean, I could map to other stuff. Like I could map to, for example, A plus BI, comma C plus DI times X, and then comma
Do you like the complex?
E, comma F. I mean, I can do that. Yeah, this would be something like, this would be C Cartesian product with, let's see here, this would be P1 over C, first order polynomials over C. Oh, it's not even that, it's worse than that. This is,
Could you just choose C?
this is XC. Ooh, that's a, sorry, that's a, let me put a Y here. There, that's better. And then Cartesian product with R, with Cartesian product with R. I mean, that would be what this is. There are infinitely many choices of ways of assembling, maybe not infinitely many. There's lots and lots of examples of 6-dimensional spaces from the things we looked at. There are many flavor choices. Yes?
And for that last one you just did with the complex Cartesian product thing,
Mhm.
prove injectivity for that one, you'd have to set each one of those, you'd have to set the whole thing equal 0, so each one of those things would be equal to 0 individually, and then that would prove that.
Oh, to get injectivity of this?
Yeah, to
map
show
like this
that
one?
the kernel of
Yeah.
P is.
Yeah, I think it's almost immediate. Once I set that equal to 0, that means this is 0, that's 0, this is 0, and that's 0, which is only true of A, B, C, D, E, and F.
I wanted to ask if there's anything like, because I know with the polynomials, like we have that theorem, like, and then the matrices is pretty, but is there something that would be nasty to use the kernel for that you shouldn't try, or?
I don't know. I mean, it's a basic theorem. Some examples are nasty however you approach them. I mean, so. I don't really put blinders on with the kernel theorem. I think it's useful wherever it's useful. I don't know counterexamples of the kernel being useful right off the top of my head. How about this one? Do you guys have any trouble with this one? I think you guys were good on this one, actually. I graded this one. A lot of you had this pretty much right. Yeah.
Can you scroll down a little bit?
Yeah, sure.
Oh, actually, no, it's right. Turn on. Why do you do B1 cross 0 union with 0 cross B2?
Because that's how we construct the basis for the Cartesian product. We take the basis for the first one and Cartesian product with 0, take the basis for the second one and Cartesian product on the other side. And you just put those together, that gives you a basis for the Cartesian product. We have proved this in general when we talked about Cartesian product. It was the day we talked about internal and external direct sums. I did at the start of the class, I proved that you could take a basis for B and a basis for W and string them together like this.
So what you're doing is you're basically taking one element, which is like B1, 0,
Right.
and then adding 0, B2.
Right, x squared with the 0 for the 2 by 2 matrices, and then the 0 for the 2 by 2 matrices. This is the basis. These two taken together is a basis for the first thing because they can get constant with 0. And then the other thing, the symmetric 2 by 2 matrices, you got 3 dimensions. This is a basis for it. So I just have those with 0 for the polynomial piece, and those just. And then the total dimension is it's additive, right? Like you add them. Yeah.
So is the dimensions of V1 cross V2 the dimensions of V1 plus the dimensions of V2?
Yes. That is true.
So,
For example,
is that
if you want to know the dimension of R2, Cartesian product with R2, it's 2 plus 2 is 4. Or R cross R is 2-dimensional, it was 1 plus 1 dimensional, so forth and so on. So this actually has been with us from pretty early on, where I was using the word dimension as if it meant something, even though we hadn't defined it yet. You know? But you guys accept dimension meaning something before you have linear algebra, right? I throw that word around in other classes and people don't really complain. You have some kind of idea of what dimension means, right?
We didn't know any better.
You didn't know any better? Well, I think the better, I guess the thing to say is now you know better, right? But you shouldn't, I mean, I think people should still be allowed to use those words even if they don't fully understand them. That's my philosophy of math. I think you always hold things in imperfect understanding because we're human. So to give up on something because you only have a partial understanding is foolish.
and that partial understanding is
Only ever have a partial understanding of everything in the totality of math. I mean, some things you'll understand a lot better as you go on, but you know, don't give up on something just because you don't know some corner of it. You know, that's the wrong way to be. Yeah.
This partial understanding is known as faith, right?
Ah.
We accept it because it's faith, and this is why we accept, and I'm already tying it into a biblical worldview. Look at me, I'm helping you.
Thank you. Now you can answer biblical worldview in grade. Okay. There you go. Oh, and here's the isomorphism. So you write down an arbitrary thing, right? And then you just count your parameters: A, B, alpha, gamma, delta. I guess you probably used other letters. There it is. Sorry, I ended up starting 10 minutes late. I'm sorry about that. I will try to finish pretty fast here. I do want to leave you a few minutes for questions after this. I'm not going as fast as I hope. Almost anything will work as an example of something which is not a derivation. 2 times the function, the identity function, lots of other stuff are not derivations. Second derivative is not a derivation, by the way. And then, of course, the derivative is a derivation because it satisfies the Leibniz rule, which is the product rule, which is essentially the defining thing for it being a derivation. For those of you I complained you didn't show the set was non-empty, if you've done these two, you could argue back to me, I already showed you something was in there. I didn't feel like your memory was so short that I had to say it again here. That would be kind of sassy, but I'd have to respect it. I didn't take points off though for that so much. Yeah. Yes, sir.
Yeah, question, when you're showing the set's not empty, you have to, can't you just use a specific element for the set? Like
Yeah,
that would be-
of course, but my point was the derivative map or the identity map is specific elements. Oh, the identity map wouldn't be an example, the derivative would. That's something in the set, just differentiation
Like,
EDIs.
could you choose a specific F and G though? And-
No, F and G have to be arbitrary points. If you're proving something for arbitrary, if you're proving something for an operator, you have to prove that it holds for all functions. Just like to prove a function has satisfies some
for all.
Yeah, to prove a function satisfies some identity, you have to prove it's true for all points in the domain of the function. The domain of the function here is functions. Because like the linear transformation is taking in a function and getting it back out a function.
Okay.
So a derivation is a function valued function of functions. So like you have to feed it to arbitrary functions. You can't pick F as something and G as something
Okay.
specific.
Okay.
Unless you're after a counterexample or something that's. All right, so anyway, I take T1 and T2, two derivations. I use Schillian. Your suggestion, I use C1, T1 plus T2, because I'm lazy. And then, of course, definition of addition, you use the Leibniz property, and you collect terms back. Check it out. The linear combination of T1 and T2 satisfies the product rule again, therefore it's a derivation. So by the subspace theorem, derivations is subspace. A lot of you guys got this. I was very encouraged. Sometimes when I ask something like this, it's just abstract enough it kind of like makes your brain go, oh. But I didn't do it. I was not successful. Many of you saw through this problem. I was very happy. And I think this problem is harder than the one you guys butchered earlier in the test. The linear independence problem, like problem number 5, way easier than this, folks. Look at that one.
We're not used to dealing with numbers.
Oh. Yeah, the answer is no. It does not follow that they're equal because, like, the example that I have here is simple enough. If you look at the direct sum of the x and y axis, you get R2, right? But if you look at the direct sum of the x-axis and, well, pretty much anything else, but for example, line y equals x. Listen, guys, any two lines through the origin are one-dimensional subspaces. As long as those lines are skew, their direct sum is R2. But it certainly does not, there's no forcing one line. You fix one of the lines, you can still move the other one around, and there's no kind of cancellation there at all. You really get almost no information about V1 and V2, except that the dimension has to be the same, because this has to be equal to that, so the dimension A cancels, and you do get the dimension of V1 is equal to the dimension of V2, and so it follows that they're isomorphic, right? Because that's what isomorphism is dimension being the same.
I was able to look at that and know that they were not equal, but I didn't know how to prove that they were.
That is good, but I need an example. Some of you guys kind of gave me like a family of examples, which is, that is on the road to the answer, but that's not the answer. Like, a counterexample must be a specific counterexample. I mean, it's not, I would give partial credit for a family of counterexamples, right? But full credit will occur if there is a clear counterexample. So like, I don't know, sometimes I take points off, sometimes I don't. It kind of depends on the quality of the family of answers that you've given me. Hard to quantify that. Okay. Problem 15. Hey, lots of you got it. Some of you didn't. And those of you who didn't, you best think about why you didn't get it. If there's an X, right, that's not a good sign here. So, all right, so basically my issue is this. You're trying to prove something about the intersection, right? So what you have to do is you have to pick a point in the intersection. So you should say that, like, or a couple points, right? So like here I say C1 is a real number. I don't know why I use C1. It's because I put a 1 later somewhere and then I went back, put 1s on everything else. I don't know. For the reason I start reading C1. I could just write C. I don't know why I have C1 here. Stupid. X and Y, I'm not a white out, it's part of the reason. But X and Y are factors in the intersection, right? I have to pick them from there. I'm trying to prove something about this set. I can't pick X in V1 and X in V2, right? If I do that, I need to explain immediately thereafter that the reason I'm doing that is because I'm looking for an arbitrary point in the intersection. Those of you who write x in V1 and x in V2 start with, and then later come around to saying, so, therefore, x is in the intersection of V1 and V2, questionable at best, this presentation, right? Because it looks confused. It looks like you're starting with V1 and V2 and you're going to the intersection. You should start with the intersection. You're trying to prove something. You're trying to prove the subspace theorem for the intersection. So you should, that's your W, right? You pick points in W, and then you try to show that a linear combination of those is again in W. All right, that's what I'm complaining about most of you if I've written a lot on your paper. It's like there needs to be this progression of ideas. Take a point W, use properties of W then to show that a linear combination of those 2 points is again in W, and then by subspace theorem, it's a subspace, although we do need to also show what? It's not empty, right? And technically it's a subspace. I mean, subset. Michael's the only one in here who showed a subset. The rest of you just assumed that V1 intersects V2 with a subset of V.
I thought we switched to.
And I didn't complain about that though, because I do expect you to assume that, so it's okay.
You, okay, you did.
So I'm saying Michael was being very picky there, and I liked it, but at the same time I didn't want to encourage it, so I didn't give you bonus points.
Thank you.
I mean, that's the sort of thing my solutions for the undergraduate were filled with, like. But anyway, what was your question?
You answered it.
Oh, okay. I didn't answer your question.
If you choose an arbitrary element in like the intersection, aren't you assuming what you're trying to prove?
No, I mean, how do you use the subspace theorem? You have to prove that if you pick 2 things in the subspace, the sum of them is in the subspace again, right? And a scalar multiple of them is in the subspace again. That is the subspace theorem. Think about subspace theorem. It's important. All right, enough about the quiz. Do you guys have questions about the test? Yes?
What time are you gonna get it at?
Oh, that is actually a very good question. When should I end it out at? Okay, so would you like?
11 o'clock.
Not
Today.
I imagine, I
10:30.
imagine that the good majority of us are willing to sneak out of Convo
Yeah,
early,
you could
so how
start
about
at
10:45?
I can
10:30.
let's make it 11:10. I think everybody should be able to get over that. 11:10.
So 11.
And you might be here early, people who were here earlier.
Would it be?
I'll be here at 11:10.
I'll be here at 10.
Yeah, I can start
I'll
at
be here at
11:10.
10 too, Lindsay. I'll wait.
It will end at 12:15.
Listen guys, I don't see this test being super long. I see it being short, and I'm looking for concise.
Did you feel the same way about test 1?
I did not feel that way. I mean, test 1, the topics on test 1, if I gave you 2 pages and gave you hours and hours and end, if you care, you should get those problems right, period. So there is time pressure in test 1, because part of test 1 is trying to convince you that you need to learn these techniques, as opposed to always just falling back on solving equations for everything. Because you can always fall back and solve everything with equations. That's true, but it's not the right way to be. You need to use the CCP and all that stuff, you know? But this one is a little bit different, right? I might give you an example and say, is this a subspace? Is this a vector space? Is this a linear transformation, you know? So those, there may be some, maybe it'd be like some rapid true or false kind of questions. And then I'll have some other ones that are more like, for example, this kind of thing, you know, prove intersection of subspaces is a subspace, or prove or disprove union of subspaces is a subspace, or, you know, is the upper half plane a subspace? Is the upper half plane a subspace?
What? What's enough?
Yes, it is.
Dr. Skimbourdis asked real analysis if the upper quarter plane was a subspace, and they said yes. Yeah,
Because you can
I told you it was. I told you it was a story. I see what you did there, but so if this is B, where's minus B?
Down.
It's over here, right?
It's not at.
It's definitely not closed under scalar multiplication. It might be closed under vector addition, actually. That's true. This is an example of a subset, which is closed under addition but not scalar multiplication.
There's no additive inverse.
Right, I mean, exactly, there's no additive inverse. This has similar problems, not a vector space.
Are the positive real numbers a field?
Yeah, no.
No? Okay, because I was gonna say you could just make your field positive real numbers.
I don't believe, no, positive real numbers are not a field because they have to have,
Oh, yeah, there's no inverse.
they have to be additive inverses, yeah.
If you asked for something like that on the test, would you include some sort of numerical definition? I guess I have trouble if you just say the upper half of the real
Oh,
numbers.
no, I will write set builder notation for the thing, yeah, I
Okay.
wouldn't just leave it upper half plane, no. No.
Or even worse, if you were to just draw a picture.
I would just write,
Oh, that's trouble
I
so
mean,
much.
it would appear like this, it would be like bracket x comma y such that y is greater than
Okay.
0. That
Oh,
would be what you'd see there.
Okay,
And I might put in, I might call it h
okay.
for various OCD reasons. You know, coordinate change, I haven't said anything about coordinate change today, but it's something we covered and we spent a lot of time on. So those diagrams and stuff, I might ask a question about those things. I prefer to ask a question about diagrams more than actual problems, because actually to flesh out an actual coordinate change problem sometimes can be kind of a pain. I wouldn't rule it out, but if I commit to that, calculationally, it's a big part of the test, right?
And we only have an hour.
Yeah. But I definitely, I mean, there will be proofs, right? I mean, most of this test is proofs, more so than the first one. This is the most proofy test in the course, yeah.
Can I ask about one of those proofs?
Yeah.
There's that proof of like, if, I don't even have to remember, but V naught is subspace of V, then you have, L V naught is subspace of W, if there's something that has to be a W.
Right.
There's the inverse of that.
Yeah, that's a good example of a possible test question, yeah.
Could you go over the backwards one?
No, we're almost out of time. I mean, it's in the notes, proof is there.
I mean, I've looked
We'll talk about it, but, you're saying the inverse image of a subspace is a subspace, I mean, so.
yes.
I can talk to you about after class, but, I mean, one thing I was saying is, there's all kinds of nice little proofs that we've gone over in class, right? And that are in the notes. Like what Landon was just talking about, the image of a subspace is a subspace, right? Or the inverse image of a subspace is a subspace. And the proof there is really little more than the definition of image and inverse image and the subspace theorem, right? Now, why wouldn't I put that on the take-home quiz? Right, because you could just go to my notes and copy it down, and or you wouldn't, and then I would be sad. So either way, it's a loop. It's like these loops for me grading. And there's, the notes are full of these little, like, you know, half-paragraph proof things. So pretty much every one of those is fair game.
Like your notes are like those for class, or like all of the above?
Yes. I'm mostly thinking of, I mean, stuff that I covered in class is, of course, most likely.
Most likely.
Mhm.
So it's over chapters 6 and 7.
It's over part 2, but of course part 1 is necessary because, well, you know, you still have to solve equations. And it's nice to know CCP if I actually asked you something with teeth, you know. Yes?
If I were to memorize every single, like, reasonably lengthed proof in the notes, how much would that boost my grade?
48%.
Probably it won't, because it's just simply not possible to memorize all the proofs of the notes.
You underestimate me, Dr. Cook. I suck at math, but I can memorize things.
It's not a math, why do you have
Yeah,
It's
like
a
some
horrible question.
Because you can
On several levels. Like, number one.
you, him, and that kid over there, like.
See, now that you've told me this, I'm going to be looking at your proof going, did he actually understand this, or did he just memorize it? You should never have told me that, because now I'm on alert.
Well, I'll just
Just
memorize
tweet
every
one
word
thing.
in the proof, so you can't count me wrong then.
I really think, in terms of memorization, the safest bet, the thing that you can't live without, it's like, you know, air to breathe or water to drink. Definitions, like you must know definitions of linear independence. And when I say definition, I really mean the set 0 equals 0 thing, right? Spanning, what is the span? What is a basis? What is a coordinate map? You know, these sorts of things you must know. Because if you don't know them, you can't prove stuff, right? Now, for the thing Landon was asking about, the thing you need to know is what's the definition of an image? What's the definition of an inverse image, right? Which is stuff you're supposed to know from 200 or 250, but in practice you guys forget, you know. Certain theorems you gotta know, right? Like inverse, you know, show injectivity, it suffices to show kernel 0, that's so important. But anyway, I think I've talked enough. I think you've suffered enough. So, I mean, until Friday, of course, but if you have questions, you know, email me. Do not despair. This test should be relatively easy if you know those definitions and can make arguments like we made in class.